Today, class, we're going to talk about the leaking water problem, and it's got several different sort of variations. We'll start with this one. I'll tell you a little bit about some of the variations. All right, so water is leaking out of an inverse conical tank. That inverse means upside down, at a rate of 0.1 inches cubed per minute. The tank is 20 inches in height and 16 inches across. Across means diameter. How fast is the depth of the water changing when the depth of the water is 10 inches? Okay, so just a couple of key things. How fast is the depth of the water changing? All right, let me underline that part. Because it mentions depth twice in this little last sentence here. So how fast is the depth of the water changing? They're asking about dH dt. Depth and height here are going to be the same thing. Okay? Okay. Okay, so how do we get started on this? So here's a picture of the tank. So you see 16 across up here, 20 is the height. There's some water in it and it's leaking out. Okay? So the first thing we're going to do here is we're gonna take our mathematical axe and we're gonna chop a cross section, okay? And we're gonna draw what it looks like. So that's gonna be basically sort of two triangles. Okay, so here's the water level and here's the top of the tank. All right, and as far as the information goes, let's go ahead and draw a perpendicular all the way through. All right. So the deal is, here's the water level, and we're going to have a radius at that point, and we're going to have a height at that point. And we also know that the height of the tank is 20, and the diameter was 16, so the radius here is going to be 8. And we want radius instead of diameter because that's all our formulas have radius instead of diameter. Okay, so we know the basic formula for volume of a cone is volume equals 1/3 pi r squared h. And the idea here is we're going to take a derivative of this, okay? But we know a couple things. So we know dV dt equals negative 0.1. Okay, I say negative because it's leaking out, so the volume is decreasing. So we know that, and we were looking for dH dt, so there's an r in here, and we don't know anything about dr dt at all. So what we're going to have to do is we're going to have to get rid of the r. So how do we do that? Well, we come back over here to our cross section that we chopped in half, and we see that we have basically a big triangle there and a smaller triangle here, or you can look at just half of it, either way. And these lines in essence should be parallel, and since they're parallel, that means that these two, the big triangle here and the little triangle here, are similar. So we're going to use triangle similarity. Alright, so we're going to go little to big, so the radius over 8 should be the height over 20, and that's just, you know, the sides are proportional if you have similar triangles. And we want to get this thing in terms of h because we're looking for dH dt, so we want to get rid of the r, so we solve for r, and 8 over 20, so we multiply by 8, get 8 over 20, and that means r is going to be, when we reduce that fraction, that's going to be 2/5 h. Alright, now we substitute that in for r here. Okay, and we're going to get that 1/3 pi 2/5 h whole thing squared times h. And when we simplify that, we're going to get the volume as 4/75, because that's going to be 4/25 pi h cubed. Alright, so let me copy that over at the top of this side so we'll have some room. Okay, and so volume is 4/75 pi h cubed. Now that's the majority of the work, to be honest. The rest of it's kind of downhill. But the key thing I want to say in addition to this, they're asking you for the HDT, and I know a real big habit of students is to solve for what they're asking for so that you just have the derivative sitting in front of you. But I'm going to write a big do not solve for h. Do not solve for h. They gave you enough information, we can find DHDT without solving for it. We'll solve for DHDT with numbers. It'll be easier. All right, so we're going to take a derivative, and we're just going to remember this is a related rates question. So what we're trying to do is relate dV/dt to what variable its volume is related to, which is h. So the dV/dt is dV/dh times dH/dt. So we just need to calculate this stuff. So dV/dt, our first calculation is derivative. So we're going to multiply by 3 because the derivative of h cubed is going to be 3h squared. And that 3 and the 75 would cancel, and we're just going to get 4/25. We're still going to have our pi and h squared. And we don't know what we're trying to find here, dH/dt. And now we're ready to plug stuff in. Okay, so we know dV/dt is -0.1, and we know h at the point in question is 10. So back over here. So -0.1 equals 4/25 pi 10 squared dH/dt. Okay, and look, that's going to end up canceling. That's going to be 100/25, which is just 4. So all of this over here is going to be 16 pi, and we're going to divide that by 16 pi. So -0.1 divided by 16 pi equals dH/dt. And we want to do a couple other things maybe. This already got a decimal in it, so I think maybe we should decimalize everything, so we'll do that. And we need to stick units on it. So dH/dt equals, so when I did that and when I punched it into my fancy schmancy calculator, I got -0.002. And how is the height measured? It's measured in inches, so the rate is going to be inches per minute. And there we go, we've solved the problem. Now, just before I leave here, so the leaking water problem, it's got several different variations. You can have all kinds of different tanks. So you can have a horse trough, for example. That's, the Cowboys shoot out and somebody hits the horse trough and water starts leaking out of it. So that one also has a cross section. It has a fixed length, but the cross section is going to be, once again, triangles. The other ones I've seen are where it's an upside down isosceles trapezoid. Once again, the cross section, it's going to have a rectangle part of it that's kind of fixed, but it's going to have the side parts that are going to look just like this, where you're going to take the radius and the height and make a similar triangle and figure out how to write the radius in terms of the height. Or maybe not radius, but some other kind of length. So pretty much all of them have something to do with similar triangles like the one here. All right, next time, toodles.